Hi everyone, today we're taking a look at memorizing transformers, a paper by a bunch of authors from Google. This paper focuses on the problem of extending the context of language models. Typically, language models such as GPT-3, BART, T5, and similar type of sequence models are limited in the size of the context they can process. This limitation is due to hardware constraints by GPU memory, basically. For example, these models can process 512 up to 2048 tokens typically for the really large models such as GPT-3. This is a problem when the target is to model tasks that require very long sequences, such as modeling whole books. For example, for books, imagine that you are generating the next sentence of a chapter. It might be beneficial potentially to be able to refer to a sentence 4 chapters back, which contains important information that will help you to generate a fluent next sentence. And another example where long sequences would be beneficial is when processing source code. Similarly, then being able to refer to information in the history, far away in the history, could be beneficial to generating better outputs. This is a pretty popular problem in NLP, and people have been trying to come up with workarounds to this issue for quite a while now. The majority of papers on this topic have focused on quantization methods or sparsifying approaches aimed at extending the context and by reducing the precision of the model, basically allowing the model to process more sequences, but at the end of the day, the model will process fewer tokens still within this 2048 limit. Some of those papers which you might have heard of, and I think I have covered a few of them also in this channel, is the logformer, performer, and reformer. All of those are targeting the same problem, but in a different angle from the current paper we're looking at today. So in the current paper, the authors propose memorizing transformers, an architecture that is targeting the similar problem, but in a much simple way and in a quite an elegant way, if I must say. So what do they do precisely in this paper? As you may be aware, the standard transformer stack architecture for language modeling or sequence modeling is containing a bunch of layers, such as an embedding layer, local attention, and feed-forward layers, which are stacked. There's many of those stacked on top of each other. And then there's softmax at the end, generating a prediction over the vocabulary to generate the next token. And there's always, for language modeling, this is always done in a sliding window fashion. So you take 2048 tokens and then you predict the next one, and then you slide by one. And the attention is always local, meaning that it's always focusing on the 2048 tokens seen currently by the model, and the model is unable to see, let's say, 5,000 tokens in the past, or even 50,000 tokens. It could be useful to be able to do that. So this is basically the problem that we're dealing with. And how the authors of this paper go around this or propose a solution to this is to integrate a k-nearest neighbor lookup cache in the attention step. So what does this do precisely? This basically what the authors do is they accumulate the hidden states of the model at each generation step. So here, let's say for this sequence, we have generated some hidden states here, 6 hidden states. And instead of discarding them as the standard model would do, this computation that has been, we spend a lot of time computing these hidden states. Instead of discarding them, what the authors do is they take those hidden states and they add them to a cache. And they do this for each generation step. So each generation step, they come up with 2000 hidden states. They store them in a cache of a fixed size. So the cache will be occasionally limited, so it will be cleaned up to make sure that it's not like too full. But we're gonna store all those hidden states in the cache, and we're gonna add a k-nearest neighbor lookup mechanism on top of them. What this k-nearest neighbor lookup mechanism will do is gonna be able to fetch a number of those cache states, and it's gonna input them to the attention mechanism, and those hidden states will be combined with the local hidden states, which have been produced basically in the previous step. And this combination will then be used in the model. So then we have a fusion of hidden states from the history that were generated long time in the past and hidden states generated right now. And this actually seems to be working quite neatly. It is a method that doesn't require sparsifying the model. So you're getting the hidden states and you basically use the k-nearest neighbor search to really get the precise hidden states that might be useful for the next prediction. And you integrate them into the local hidden states using a gated mechanism that the authors introduced. So basically the model is able to decide at each step how much from the KNN cache it should use versus how much of the local local hidden state it should use. Then it's able to fuse this information and produce better outputs. So this is the basic idea. It's quite a simple approach and seems to be effective. This is the only math that they introduce, or of course there's some logic regarding the KNN model, but the KNN is a standard model, basically approximate nearest neighbor search. I believe they use FICE or a similar KNN library. And basically this is how it works. So you have a gate here, like a parameter parameter G gate, which controls how much of the memory versus how much of the local hidden states should be used. The memory here is the output of the KNN model. And that's basically it. And this model can then be fine-tuned. So what the authors do in the paper is they take a pre-trained model and they augment the attention using this KNN cache. And then they fine-tune for a little bit to see if the model will be able to use those hidden states and integrate them. And it seems to be quite effective, and it seems to work. If we take a look at this interesting graph, for example, where they have plotted the number of training steps on the x-axis and the perplexity of arXiv math paper dataset, what they observe is that the model with memory achieves much lower perplexity than the baseline if it's trained from scratch with this KNN cache. But even the model that has been trained without a cache and then has been fine-tuned with a cache for some steps, even that model is able to reach the same accuracy as the memorizing transformer model. So it seems that the model is able to use this cache, and because the hidden states are produced by itself, so the model has produced the hidden states in the cache, it's able to integrate them and use them effectively to achieve better results. So this is basically the main gist of the paper. The authors also perform a bunch of other experiments on other data sets showing that the memory can be used and seems to help in overall. And furthermore, they perform some analysis on the memories that were retrieved by the model to show that there is some meaning behind what the model has learned in terms of how it's retrieved the memories, which memories it retrieves, and how they could be useful for the current generation. That is the main thing that I wanted to cover for today. I hope this was useful. Please like and subscribe, and I'll talk to you in the next one.